Okay, so good afternoon, all. Welcome back to the weekly live sessions on wheeled, mechanics and control of robotic manipulators. So I hope you have been going through the courses so far. I hope the journey has been smooth until week 3. So today we'll be discussing a summary of the lectures that Professor Shantakumar delivered for the contents of week 3. And we'll also discuss some sample problems that may also help you to solve some of the tutorial problems. Okay, so introducing myself, I'm Isaac John. I'm a PhD scholar from IIT Palakkad. I do my PhD right under the supervision of Dr. Shantakumar. So yeah, that's about it. We'll get on with the session if you don't have any questions. Okay, so for the week 3, this is basically a direct continuation of week 2. So as a recap, we have discussed how to derive the DH parameters, how to assign frames on a given manipulator. So all the relevance, the basics of kinematics have been covered in week 2. Like we have established how to map a frame, a rotating frame with respect to a fixed frame, how to construct a transformation matrices, and what are the conventions that we follow using this DH parameters and all those things. So this week is basically an extension of week 2, where we would be actually modeling robots. We would be solving actual problems in robotics, such as this forward kinematics as well as the more important inverse kinematics as well. Yes, so these are the key sections that we have covered in week 3, which are the forward and inverse kinematics of robotic manipulators. Inverse kinematic solution based on numerical methods. Forward kinematic solutions using MATLAB. The professor has also demonstrated how to use MATLAB to solve the forward as well as inverse kinematics of robotic manipulators. He has also demonstrated how to solve the inverse kinematics numerically as well as analytically. Both methods have been discussed. And we have also seen in the lectures the advantages and disadvantages of both of the methods. So we'll summarize all these results or whatever we have come across in this week through these live sessions. Okay, so I would like to discuss some key terminologies. The first being what we call the forward kinematics. We have already defined these, we have already come across these terms in the previous weeks, but since this is very relevant to our course, we are simply recalling the key definitions. So basically what forward kinematics says, it determines the configuration of the end effector, or in other words, the operational as well as task space variables for a given relative configuration of each pair of adjacent links, or in other words, configuration or joint space variables of the robot. So it's a very lengthy statement, but to make it concise, I will give you a brief demonstration. So as again, we would limit our examples with 2R manipulators, which are basically a two-linked 2 degrees of freedom manipulator having 2 revolute joints. This is the first revolute joint. This is the second revolute joint. I would be labeling the revolute joints as R1 and R2. And this being a 2 linked mechanism, this is the first link over here. The first link, and this would be the second link. And we also have an end effector rigidly attached to the second link. So this being the end effector. Right? So in this case, in the context of a 2R manipulator, we have something, the definition basically says to determine the configuration of the end effector. So since this is a 2 degrees of freedom robot, the end effector is basically defined in terms of 2 task space variables, which are X and Y, 2 Cartesian coordinates. So these are basically task space variables. Another terminology is operational space. So we would define the position, the real-time position of the end effector using task space variables. And if you want to control the robot, how would we control the robot? Because the motors on this robot, R1 and R2, are controlled by giving inputs to the specific motors. So we would have two motors over here, one motor on each of these joints. And if you want to control the position of the robot, we would be giving the inputs to the motors. And the motors are basically living in a different space as opposed to the task space, which what we call as joint space variables. So the variables of the joint space are theta1, that is the joint variable of the first motor, and theta2, actually the relative positions, where theta1 and theta2 are joint space variables. They are also called configuration space variables. So what the forward kinematic says is that, like, if it basically determines the configuration of the end effector. So if we give a set of joint space variables given theta1 and theta2, what is the configuration of the end effector? End effector coordinates. This is what the forward kinematics problem solves. Whereas in the case of inverse kinematics, it says for a given desired configuration of the end effector, find the joint space variables which achieve that configuration. So if our task is to find out the inputs to the motors, like if we want to locate this end effector at a specific x and y location, how would we want the theta1 and theta1 to be? That is the problem of inverse kinematics. So for a given end effector coordinates, x and y, what are the joint space variables, theta1 and theta? This is what the inverse kinematics problem is all about. So I guess we are fairly thorough with the concept of forward and inverse kinematics and what problems that they are essentially trying to solve. Basically, in essence, like forward kinematics is more or less used for simulating the mechanism, more or less simulating the mechanism, whereas the inverse kinematics are mostly used for controlling the robot. Right? Because like in the case of forward kinematics, given theta1 and theta2, what would be the final position of the robot? That is more or less simulating the robot. But if you want to control a robot, if you want to make the end effector go to a specific x and y point, what input should we give to the motors? What inputs theta1 and theta2 should we give to the motors? So that is exactly the problem of controlling a robot. So that is basically the problem of inverse kinematics. Yes, and moving on formally to the forward kinematics, it is basically the transformation of kinematic information from robot joint variable space to the Cartesian coordinate frame of the final frame. Right? So here the inputs would be, in the case of forward kinematics, the input would be the joint space variables theta1 and theta2. And we would use some transformation. So here the transformation is nothing but the forward kinematics to obtain the final task space variables x and y. That is what the first sentence says. And the second point says the traditional way of producing forward kinematic equations for the robot manipulator is to proceed link by link using DH notations and frames. Right? So what exactly it means is that, like, again, from the context of a 2R robot, this being the first link and a second link, there are first revolute joint, the second revolute joint, first link, second link. So what we would use is based on the DH parameter convention, we would assign frames. We would, roughly speaking, we would have how many frames? Since this robot has two rigid bodies, how many frames we would have. So for a robot with n degrees of freedom or n rigid links, number of links, the number of frames as per the modified DH parameters would be n plus 2, right? 2 for each of the links and 1 for the ground and 1 for the end effector. So it would look something like this. We would have Z0, the frame Z0 like this, X0 like this. Z1 will also be coincident with Z0. X1 would be along the link length of the first link. This would be X1. And Z2 would be at the location would be at the second revolute joint. And the direction of Z2 would be normal to the plane of the board. And X2 would be along the link length 2. And we also have one more frame, Z3, X3, right? So what the second statement says is that, like, once we have figured out how to attach the frames, we would have to again construct the DS parameter tables. Then after that, what we would require? Like a DS parameter table would help you to compose a matrix like this, transformation of ith frame with respect to I plus 1th frame. This is basically a 4x4 matrix. So using the DS parameter table, you would be able to assemble this matrix, the transformation matrix. And what again, like how does this come in relevance to the forward kinematics problem? So using this DS method, we would successively find out the transformation between the 0th frame and the first frame, the first frame and the second frame and third frame, right? We would have all these informations from the DH table. All this information we can obtain from the DH table, right? And within the transformation matrix, these are all functions of the joint space variables, because as you might know, one of the DH parameters are the joint variables. Like if this is theta1 and theta2, the theta1 and theta2 are essentially one of the DS parameters, and they would all be embedded in these transformation matrices, right? And if you want to obtain the final transformation between the base and the end effector frame 3, you would only need to multiply all the individual transformation matrices in this order: 0 to 1, 1 to 2, and 2 to 3. If you do that, you would get the final transformation matrix of the end effector, which is the frame 3, with respect to the base frame. So again, this is basically the forward kinematics problem, because this would be the 0 T3 would be a function of the joint space variables theta1 and theta2, right? And if you give inputs, if you give any inputs to these specific theta1 and theta1 values, you would get a different the components of the matrix 0 T3 would be varying as you vary theta1 and theta2. This is basically how you do this forward kinematics. So if you want to know the final position of the end effector, you first obtain this matrix 0 T3. And as you might have recalled, a transformation matrix, the first, it comprises of a block, a 3x3 rotation matrix, and it comes as a position matrix 3x1. And at the final row, you will have all zeros and 1. And if you want to extract the position of this RR robot, you only need to extract this portion of the robot, this portion of the final transformation matrix. So if you have managed to assemble this matrix 0 T3, simply by extracting this portion of the final transformation matrix, you will be able to exactly locate the final X and Y points of the end effector. Right. Coming on to the third point, hence the forward kinematics is basically the transformation matrix manipulation. So like if you have figured out how to get this transformation matrix, it's only a matter of multiplying individual transformation matrix. Individual transformation matrix in the sense like from the 0th frame to the first frame, right? And from the first frame to the second frame, and from the second frame to the third frame. So once you have assembled all the individual transformation matrices, you multiply them together so that you will be able to obtain the final configuration of the end effector. So that is what the forward kinematics problem is. It's fairly straightforward for a serial manipulator. Yeah. And again, like we have also discussed a convention of how to name or how to fix the frame on the end effector. Because like earlier, if you take the context of a 2R manipulator, we know basically how to assign. We basically know how to assign each of the frames using the DS parameter convention, because the DS parameter convention basically says the Z axis should be along the axis of the rotation of a revolute joint, or it should be along the direction of the prismatic joint, and the is X joint would be should be along the common normal between the current Z axis and the subsequent X axis. So all the notations and all the terminologies are available for the frames for each of the active joints. But what about the frames of this end effector? So basically, we can attach a frame of reference however we want, but there are basically specific naming conventions, right? So basically, what it says is that, like, again, like the end effector again would have three axes, X, Y, and Z axes. And if this is the plane of this end effector, I hope, yeah, if suppose this as an end effector, right? And this is how we would fix the tool. So for example, if I am fitting a tool like this, maybe a welding torch or something, for example, if this is a tool, for example, like if this is the longitudinal axis of the tool, this could be something, maybe a drill bit or a laser cutter or anything for that matter. And with respect to this end effector, there are three specific directions. So one of the important direction is something along the longitudinal axis of the tool. So if this is how the tool is fixed, the longitudinal direction at which the tool is fixed is called the approach vector. So this is how a robot or the end effector would approach a workspace. So if you want to drill something or if you want to fix something, the end effector would be approaching along this direction. If this is the tool, and if we have a surface over here to be laser cutted or machine, the direction at which the end effector advances to the tool, which is this direction, is called the approach vector. Right. So the first statement basically says that the approach vector is aligned with the tool axis and points away from the wrist. Right. So we know the direction of the approach vector, that is this direction, and it also says it should point away from the wrist. So the direction is exactly this. It cannot be this. It cannot go the opposite direction. As it says, by definition, it should point away from the wrist. This is how the approach vector would be aligned. Then we have something called a sliding vector, which is orthogonal to the approach vector and aligned with the open and close axis of the tool. So if this is a gripper, the gripper would open and close along this axis, right? So if we are moving these jaws further apart along this direction, we can take the tool out. And if we are bringing these jaws together, we would be able to clamp the tool. So by definition, the sliding vector is basically orthogonal to the approach vector. So this is the approach vector, this is the sliding vector, and there is a 90 since this is orthogonal, there is 90-degree difference between the sliding and approach vector, and it is aligned with the open and close axis of the tool. Sometimes it is also called orientation vector of the tool. So another name is this another but less commonly used name is called this orientation vector. And now that we have two vectors, the third direction, what we call as the normal vector, that is normal to the plane of the gripper, can be determined using the right-handed thumb rule. So yeah, the normal vector is basically orthogonal to the plane defined by the approach and sliding vector. So if this is the plane, one second. Yeah. This is the plane defined by the approach and normal vectors. This is the plane. Orthogonal to the plane is what we have, the, the, the normal vector, actually, the normal vector, right? Yeah, that's about it. So whenever we are specifically defining the pose of the end effector, people would mostly define the pose in terms of normal, approach, and sliding vectors. So in this regard, we should be aware of in what all direction these vectors are aligned. Normal vector is, the approach vector is aligned along the axis of the tool. The sliding vector is aligned along the axis at which the gripper opens and closes. And normal vector is basically orthogonal to both the approach as well as sliding vectors. So like in short, we denote these as normal, approach, sliding vectors as N, S, A unit vectors, right? And if you can recall, while if we assemble the rotation matrices, 3x3 rotation matrices, we would assemble in this form. N matrix would be, the first column would be Nx, Ny, Nz. The second row corresponds to the sliding vector Sx, Sy, Sz, and the third column corresponds to the direction cosines Ax, Ay, Az. So like we know basically this is basically from the earlier definition of rotation matrices, we know this corresponds to the direction cosines of the new x-axis with respect to the fixed x-axis, and this corresponds to the new y-axis, the rotated y-axis with respect to the fixed y-axis, and this basically corresponds to the direction cosines of the rotated z-axis with respect to the fixed z-axis. So in that regard, this normal vector corresponds to the x-axis, the sliding vector corresponds to the y-axis, and the approach vector corresponds to the z-axis. So this makes perfect sense because like in other conventions, in machining conventions and all the other conventions, we already know that the tool is basically aligned along the z-axis, right? So that is one of the conventions that we would employ here as well, using the normal, sliding, and approach unit vectors. Okay, so coming on to the problem of inverse kinematics. So far we have covered forward kinematics. That is fairly straightforward. Like it's only a matter of multiplying the transformation matrix. But in case of serial manipulators, the problem of inverse kinematics is a bit more involved, a bit more complicated. So what it says, it's the problem of determining the joint space variables of the robot for a given configuration of the robot. So like, as we have already discussed, like if you want to position the end effector at a specific point, what should be the joint variables of the robot? And the second point says determination of the joint variables in terms of end effector position and orientation is called the inverse kinematics. So for a 6 degrees of freedom robot, the end effector's position is defined by 3 variables, x, y, and z. So these are end effector position variables. And the orientation of the end effector would be defined by 3 other parameters called phi, psi, theta. It could be anything, but we need 3 independent parameters for end effector orientation. Variables. And all the 6 parameters in collective together are called as task space variables. So if we want the robot to achieve this specific set of task space variables, what would be the joint space variables? So for a 6 degrees of freedom robot, we would have to find out all the 6 joint variables of the robot, right? To realize this specific set of task space variables. So that is the problem of the inverse kinematics. Okay, coming on to the third point, it says, although there are no standard and generally applicable method to solve the inverse kinematics problem, there are a few analytical and numerical methods to solve the problem. So it's not as easy as solving a forward kinematics problem. The inverse kinematics problem is specific to the robot. It's not universally applicable. So the solution basically depends from a robot to robot. You cannot apply one methodology to suit all such robots. So in case of a robot with a fewer number of joints, you will be able to find out the solutions analytically. For example, a 2-hour robot or a 3-hour robot, it's possible to solve it analytically. But in case of a robot with more number of joints or a higher axis robot like a 6-hour robot, you may not even solve this analytically. You would have to employ some numerical methods to solve this problem of inverse kinematics. And again, the main difficulty of inverse kinematics problem is the existence of multiple solutions. So I'll give you a brief example. So again, if you consider the example of a 2-hour robot, it can have 2 solutions. So let this be the workspace X and Y. I hope you can see this. And for realizing this specific point in the workspace X and Y, a 2-hour robot can achieve this in 2 ways. So this is one solution. So this is one revolute joint, this is another revolute joint. And there is one more solution possible to realize this end effector coordinates. You can also achieve using this solution as well. Right, so there are 2 solutions. So typically this is called an overarm solution. So if you take an elbow of a human, this corresponds to an overarm configuration of the elbow, right? This solution corresponds to the overarm configuration of the elbow, and this solution corresponds to the underarm solution of the elbow. So like for a given, the inverse kinematics, so the problem of finding the configuration of the robot for a given XY position can lead to multiple solutions. It can have multiple solutions, this being the first solution and this being the second solution. So a robot as elementary as a 2-hour robot has multiple solutions. 2, in fact, for this case. You can imagine how many solutions a 6-hour robot can have for a specific end effector pose. It can have multiple, meaning more than 6 or at least 6 solutions for a given end effector pose. So that is one of the difficulties of analytical inverse kinematics, the existence of multiple solutions. Okay. So we'll also discuss a few more important points. So the first being the computer controlled robots are usually actuated at joint space variables. So as I've already mentioned, if you want to control a robot, you basically control a robot by giving inputs to its motors. So the motors are typically located at the joints R1 and R2. So the inputs given to the motors would be in terms of the joint variables. Here, inputs given to the motors would be in terms of the joint variables. And yeah, however, coming on to the second point, it says, however, the objects to be manipulated are usually expressed in the Cartesian coordinate frames. So if you want to manipulate an object, if you want the robot to grip an object here, if it want to manipulate an object from a position x1, y1 to some other location x2, y2. So this task is basically mentioned in terms of task space variables. It would be very difficult if you define these in joint space variables. Like if instead of using x and y, if you are using theta1 and theta2 to locate an object in space, that would be very counterintuitive. It is not at all intuitive. So we have joint space variables. So sorry, we have task space variables over here to manipulate the objects in an environment. So there is a clear need of mapping between the joint space variables and the task space variables. Because a robot is controlled using joint space variables, the objects to be manipulated are expressed in Cartesian coordinate frames. So there is a clear need to map to and fro, back and forth between the joint space variables and the task space variables. So that is exactly what the point 3 says. Therefore, carrying kinematic information back and forth between joint space and Cartesian space is needed in robotics. Now we know why, because the objects are mentioned in task space and the robot is controlled using joint space. So coming on to the fourth point, it says to control the configuration of the end effector to reach an object, the inverse kinematics problem must be solved. So if you want to move this end effector, if you want this end effector to move or to grasp this object in space, the end effector's position would be same as that of this object that is to be manipulated. And using inverse kinematics, we would be able to identify the inputs that is given to the motors. That is the problem of inverse kinematics. And as you might have already experienced, it's more difficult due to the existence of multiple solutions. And as the number of degrees of freedom increases, the equations to be solved becomes more and more complicated, right? The second point says the equations to solve are non-linear. Thus, closed form solution is not always available. So due to the fact that this equation is highly coupled, you will get to know if you try to model a robot. The equations are basically very non-linear. It's coupled, like each joint variable would be present in every equations. It's highly coupled, highly non-linear, and it's not easy to solve such problems analytically using known methods. And we have also established that there could be possibilities of multiple solutions. So the solutions are not unique, especially for a redundant robot. And we have also seen this elbow up and elbow up configuration for a 2R robot. So like in case of a 2R robot, right, it can basically achieve this goal position either in along this orientation, or it can also achieve it in this orientation. Both of these underarm as well as overarm solutions are possible. And the inverse kinematic solution is basically dependent on the configuration of the robot. The solution basically varies from robot to robot. Whereas in the case of forward kinematics, it is only a matter of multiplying the transformation matrix 0T1 times 1T2 times 2T3 times NT and plus 1. It's only a matter of multiplying. But in case of inverse kinematics, it is more difficult. It's dependent on the robot. How you solve the problem is basically dependent on the robot. So because of this reason, there are two different methods to solve this inverse kinematics problem. So the two major methods are numerical methods and closed form solutions. So as I've already said, like not every robot has a closed form, a neat closed form solution. Because like as the number of freedom increases, the equations become more and more complicated. It would be very difficult to solve the problem analytically. And the only other way to solve for only other method or only other way to solve such problems is numerical methods. So when analytical solutions are difficult or more or less impossible to obtain, we would come back to the numerical methods. So we basically have key differences between the results obtained using numerical methods and analytical methods. We will go through this one by one. So as far as this numerical solutions are concerned, it says the results in numerical iterative solution to a system of equations. Examples using Newton-Raphson method. So you might already know some iterative methods to solve some equations. Like we have this something called bisection method. We have this regular falsy method. We have something called this Newton-Raphson method. To find out a solution, or if we have a polynomial equation, something like this, f of x as ax square plus bx plus c, some, I don't know, some complex equations, we would use this regular falsy or Newton-Raphson method to find out the roots where this equation becomes zero using iterative procedures. Yeah, coming on to the second method, it says unknown number of operations to solve. So since this is an iterative process, we don't know exactly how many number of operations we would require. So another why, but again, why would we know? Why would we want to know the number of operations? It's always good to know the number of operations because we would get a rough idea of the duration or the cost of computation of such problems. Like if the number of operations is too high, the computational time would be very high. And if the number of operation is very low, obviously the computational time is also very low. But in case of numerical methods, the insight regarding the number of operations is it's unknown. It's not known actually. And yeah, it's not coming on to the third point. It's not dingle. It's single actually. It's a typo. It's single. Yeah. So it's not capable to numerical methods are not capable to return multiple solutions. So like as I have already explained, in case of a 2-hour robot, it cannot. There are basically two solutions, underarm as well as this overarm solutions. And numerical methods can only converge to one solution. It cannot. It won't give you both of these solutions because numeric iterative methods are mostly based on an initial guess. So like if to trigger such calculations, we would basically give an initial guess of, we would have to provide an initial guess of the solution, right? So for example, if we are given the task space variables of a robot and our objective is to find out the joint space, this is unknown and this is task space is given. And our objective is to find out the joint space variables for a given set of task space variables. And in numerical methods, we would have to give a guess, an initial guess of the solution. So if theta1 and theta2 are the task space, the joint space variables, we would have to give an initial guess, theta1 guess, and theta2 guess, an initial guess of the solution. And depending on how you give or depending on where these initial guesses are in theta1, theta2 space, the solution may converge to one solution or the other solution. So if the initial guess is closer to if the initial guess is basically closer to this overarm configuration, the iterative procedure would converge to the overarm configuration. If the initial guess is closer to the underarm configuration here, the iterative procedure would converge to the underarm configuration, right? And the accuracy is basically dictated by the user. That is also one another aspect of the numerical solution, because the iterative procedure can theoretically it can go up to infinity, and we would terminate the iterative procedure when the difference between the current solution and the next solution is a very small number. For example, if theta 1, theta 2 current estimate for a time t minus theta 1, theta 2 estimate for another time step t plus 1 is less than 0.001 or something, we can use this criteria to terminate this iteration procedure, right? And we get to choose this value. We get to choose how accurate the iterative solution should be. We can even make it even more accurate. We can even increase the number of decimals, right? So that like if the difference between two subsequent iterations are less than this parameter or this small value, we can terminate the numerical iterations. So that is what it's meant by the accuracy is dictated by the user. So we get to choose this quantity. And because of all these reasons, like we are only getting an approximate solution, it's not an exact solution. And due to the fact that it can only converge to a single solution, this is much less desirable than closed form solutions. So one of the reason is that it can only converge to one of the solutions. The number of operations is unknown, so we don't know how much time it takes to solve it numerically, right? And the accuracy is dictated by the user, so it's essentially an approximate method. So because of all these things, it is much less desirable than closed form solutions. But the positive side is that it can be applied to all robots. Numerical solutions can be obtained for any robot. So if it is very difficult to solve the solutions analytically, we can rely or we can count on numerical solutions to obtain the solutions to a degree of accuracy, right? Okay, so coming on to the closed form solutions. So it's, as it says, it's basically analytical solutions to a system of equations. So it's basically solving these equations analytically using the known techniques. And coming on to the second point, it says can be solved in a fixed number of operations. So in case of an analytical method, we get to know exactly how many multiplications, additions, divisions have to be performed. So in that regard, we know whether the closed form solution is fast or slow for a specific problem. Coming on to problem 3, it says results in all possible solution to the manipulator kinematics. So due to the fact that we are solving it analytically, we get to know all the results. So in case of a 2-hour robot, we can exactly find out the overarm configuration as well as an underarm configuration. So like, for example, like if the problem is basically solving a quadratic equation, ax square plus bx plus c, like if the solving of an inverse kinematic problem is basically equivalent to solving a quadratic equation, we know that there are two roots of a quadratic equation, right? Minus b plus or minus root of b square minus 4ac by 2. So we know for a fact that we can obtain two solutions analytically. So that is exactly what it says. So all possible solutions to the manipulator kinematics can be obtained if you are solving it analytically. But coming on to the fourth point, it's often difficult to find. So for robots with fewer number of joints, it is possible to find. But as the number of links and as the number of joints increases, it becomes a highly complicated problem and it's often difficult to find. But due to the fact that this is analytical, it is desirable for real-time control. So like you only need to solve the problem once. And once you have solved the problems, you can substitute the values so that it'll be fairly fast for real-time control. But in case of numerical, you will have to solve this for each configuration. You have to run the numerical solver every time. So it may take some time to control. It may take some delay or a lag to control a robot in using numerical solutions. whereas it would be much faster in closed form solutions. And due to this fact, it is more desirable overall, like compared with that pros and cons of numerical and closed form solutions. We prefer the closed form solutions over numerical solutions because of due to these facts. Okay. Again, like as I've already mentioned, as the number of links increases or as the number of joints and link increases, it becomes increasingly difficult to solve the problem of inverse kinematics. And a typical example would be the inverse kinematics of a 6-axis robot, which is capable of 3 degrees of position and 3 degrees of orientation. But there are exceptions to these rules also. So it says that, like, given a 6-axis robot, it can be proven that there exists a closed form solution for inverse kinematics, provided if the 3 adjacent revolute joint axes intersect at a point, and the second point, if the 3 adjacent revolute joint axes are parallel to one another, right? So, for example, like if we have a 6-axis robot having 3 revolute joints parallel to each other. So, if this is Z axis, if this is X axis, this is Y axis, and I'm representing the revolute joints as out of plane. So this is one axis, this is another axis, this is another axis, and all the 3 revolute joints here are parallel to each other. They are all parallel. And that corresponds to this law. If the 3 adjacent revolute joints are parallel to one another, so we have 3 revolute joints parallel to one another. And if the 3 adjacent revolute joints are, the first statement says, if the 3 revolute joint axes intersect at a point. So, yeah, these are the 3 revolute axes, R1, R2, R3. And we have 3 more revolute joints. So I'll denote this as R4. Let this be R4. R5 would be along this x-axis. This is R5. R5, R6 would be along the y-axis. This is R6. And note that R4, R5, and R6 intersect at a point. So that is what the first statement says. If the 3 adjacent revolute joint axes intersect at a point, 3 revolute joints intersect at a point, and 3 adjacent revolute joints are parallel to one another. 1, 2, 3. So if you come across such a situation, then you can analytically solve this problem. You don't have to rely on numerical methods. So the reason is that you can solve this problem using a pure positional problem. You can split this inverse kinematics problem into 2 subproblems. Inverse kinematics problem into an inverse position problem and an inverse orientation So when you come across this situation, as denoted by points 1 and 2, you can decouple the general inverse kinematics problem into an inverse position kinematics problem and an inverse orientation kinematics problem, where the first part of the manipulator, comprising of R1, R2, and R3, only deals with the positioning of the robot, right? Just the positioning of the robot, and the remaining 3 axes, R4, R5, and R6, only deals with the orientation of the end effector. So there are known methods, like if you have a 3R robot like this, you can solve this analytically. If you have a 3R robot where all the joint axes intersect at a point, you can also solve it analytically. So simply by decoupling this problem, you would be able to solve this problem analytically. But maybe for any other case, like if the six axis robot does not satisfy these two conditions, then it will be very difficult to solve the problem using analytical method. But this is basically an exception. The reason being, you can decouple the problem into an inverse position kinematic problem and an inverse orientation kinematic problem. So that is one of these exception for a six-axis robot. And for all the other cases, you will have to rely on numerical methods. Okay, so coming on to an example of an inverse kinematics problem, I'll give you a, a, a taste of how to solve an inverse kinematics problem of this robot. So this is an RP robot, as you can recall. So it has two joints. The first joint is a revolute joint like this, defined by the joint variable theta1. And the second joint is a prismatic joint. So the motion of this prismatic joint is characterized by the variable d2. Right? So this is nothing but an RP robot, an RP robot. It has 2 degrees of freedom. Right? And how to solve this, the inverse kinematics of this RP robot. So for a given X and Y position of the robot, how do you, for a given, I'll write the problem statement. For a given XY position of this end effector, what are theta1 and d2. All right, so again, like just by looking at this robotic manipulator, you know the equations of this mechanism, the constraint equations of the robot, which are like, for example, like if you take this as, if this direction to be x-axis, let this be xa, let this be ya. So the position of this end effector, x, y, position of the end effector, x and y are basically, it's d2 cos theta1, and y axis would be d2 sine theta. Right? This is fairly straightforward. You can basically write this equation using observation itself. But for complicated robots, for higher degrees of freedom robot, you will have to use DS parameters, right? So you will have to assign the frames. You will have to figure out the transformation matrices 0T1. You'll have to figure out 1T2. You'll have to figure out 2T3, etc., NT, n plus 1. And if you multiply all these subsequent transformation matrices, you will end up with the final equations of X and Y. So that is how it is usually done. But since this is a fairly an easy robot with only 2 degrees of freedom, we can write down these equations just by observation itself. Again, coming on to the problem, we have to find out for a given X and Y, what are the variables of, what are the joint variables, which are d2 and theta1. So by simple mathematical manipulation, if you take, like, let this be equation 1, and if this is equation 2. So if you square and add equations 1 and 2, 1 square plus 2 square would imply x square plus y square would be d square, right? And the solution for d2 is simply the square root of x square plus y square. And if you take equation 2 by equation 1. This would be d2 sine theta 1 would, and this would be d2 cos theta 1. This would be y by x. And this would further lead on to tan theta 1 would be y by x, and theta 1 would be arc tan y by x. So these are the solutions. So these are the inverse kinematic solutions of this specific robotic manipulator, right? So we have obtained the expression for D2. We have also obtained the expression for theta 1. So this is basically the inverse kinematics problem of this specific robot. So I can also show you how to solve this inverse kinematic problems of a RR robot. Should I show this, or are you familiar with this, or should I leave it for a later period? Because we have questions to solve. It's up to you. Or are you already familiar with this? Can anyone respond? Okay, okay, yeah. One of the participant has responded to uh, positively, so that we can solve the inverse kinematics of a 2R robot. Okay, so let me just construct. So yeah, I'm fairly messy with all these diagrams. So if there is any clarity issues, please let me know. So I'm defining the axes as this be the x-axis, this be the y-axis, the global x-axis and the global y-axis, and the z-axis would be out of plane. This would be the z-axis. And this is the first link. I'll label this as L1, the length of this link. So this is a 2R robot. So this is the first link. And this is the second, sorry. Yeah, this is the second link. And we have this end effector at the tip of the second link. And the position of this end effector would be denoted by XE, YE. This is the position of the end effector. And the joint variables would be theta 1. The rotation of the first link would be theta 1. And the joint variable for the second link relative to the first link is this is theta 2. And length of the first link, let it be L1, and length of the second link is L2. So our objective is to find theta 1 and theta 2 for a given XE and YE. This is our problem of inverse kinematics. All right. So how to do that? I'll just briefly write down the derivation of this problem. If you have any doubt, you can let me know. Right. So if you okay, so yeah, if the equation is fairly straightforward. So if we consider this right angle triangle, right? If you consider this right angle triangle, you should also consider this piece also. I'll also denote it as in a different color actually. So it won't be. Right. So this is just a tool. This is just a line to solve this geometrically. I'll probably shade this also. Links. first link and the second link. Yeah, and I'm labeling this line as R. So if you consider this to be a right angle triangle, if this thing is considered to be a right angle triangle, then what is R? So considering the right angle triangle, R, one second. R square is nothing but xc square plus ye square. All right. If I label this as equation 1, this is xc, this is ye, this is R. So xc square, sorry. Yeah, xc square plus ye square is R square using Pythagoras theorem. Again, coming on to this triangle, there is also another triangle. This triangle, I hope you can see that. This triangle. And if I'm labeling this angle, hold on, this angle as alpha. So using law of cosines, what is R? From the perspective of this triangle. So using law of cosines, yeah, R square is nothing but L1 square plus L2 square minus 2 L1 L2 cos alpha. This is equation 2, right? So we have two equations for R square. So comparing 1 and 2, comparing 1 and 2, we will have this equation xc square plus ye square is nothing but L1 square plus L2 square minus 2 L1 L2 cos alpha, right? So this is one of the key equations. I'll write this as equation 3. And now our objective is to make a relationship between alpha and theta 2. Because our objective is to find, one of our objective is to find theta 2. We already got an expression relating xc and ye with respect to alpha 2. So then how do we map alpha to theta 2? So we know for a fact that alpha plus 180, alpha plus 180 degrees is theta 2. I hope you can all agree with this. This is alpha and this is theta 2, and alpha plus theta 2 is 180 degrees. Right? So then what is theta 2? Theta 2 would be 180 degrees. So, sorry, I think I made a mistake. Alpha plus theta 2 is 180 degrees. And theta 2 is 180 degrees minus alpha. Right? So if I substitute this back, so if I substitute, oh, okay, I made a mistake again. We have the alpha 2 over on equation 3. So alpha is 180 minus theta 2. So this is equation 4. So if we substitute this alpha as 180 minus theta 2 on this cos alpha, what will you get? Alpha as 180 minus theta 2 on cos alpha. So we'll do one thing. We'll substitute just that for cos alpha. So cos alpha is cos 180 minus theta 2. So what is cos 180 minus theta 2? That is cos 180 cos theta 2 plus sine 180 sine theta 2. So sine 180 is 0. Cos 180 is minus 1, right? This is, yeah, cos 180. This would be minus cos theta 2. right? So now equation 3, if you substitute that, equation 3 becomes xe square plus ye square is L1 square plus L2 square. Now, so instead of substituting cos alpha as minus cos theta 2, this will be 2L1 L2 cos theta 2. There is a minus in front of the cos theta 2. That minus and this minus will get cancelled, right? So this would be our equation. So cos theta 2 would be xe square plus ye square minus L1 square minus L2 square by 2L1 L2. So we got an expression for cos theta 2. So that is one part, right? So now we can find out theta 2 as arc cos this expression, this entire weak expression. We'll be able to get theta 2. So we got theta 2 as a function of xe and ye. We solved one of our objectives. Now we want to solve theta 1 also, right? If we want to solve theta 1. So theta 1 is a slightly bit more involved. I'll just rearrange these equations. You can always visit these lectures in YouTube if you want to consult this. Just to reorganize this one. Yeah. So that is an expression for theta 2. We need to find one expression for theta 1. So I'm defining two more angles for the sake of simplicity. So what ink should I use? I am using this blue ink. So this large angle, I hope you can see this one over here. I'm calling it as theta t. And one more small angle I'm defining. This is beta. I hope you can see this angle, beta. And this one is theta t. Sorry, theta t is, yeah, the entirety of this angle is theta t. This entire angle is theta t. And this small angle is beta. From the base to the blue line is theta t. And from the first link to the blue line is beta. So now theta 1 would be theta t minus beta, right? I hope you can agree. Let this be equation 4. Now what is theta t? Theta t, the solution for theta t can be obtained from this triangle, right? So that is nothing but like sine theta t. What is sine theta t? Sine theta t is opposite side by hypotenuse, that is ye by r. Cos theta t is adjacent side by hypotenuse, that is xe by r. Theta t is tan theta t is ye by xe. So theta t is arc tan ye over xe, right? This equation. So we found out theta t as a function of xe and ye. Now we need to figure out what beta is. So I'm labeling this as equation 5. Now, in order to figure out beta, you have to consider this triangle. There is a triangle like this. So I'm again using this blue marker. I am projecting one perpendicular line from the tip of the center effector. So the new triangle to be considered is this one, this blue line R, this portion, and this portion. So if you take a look at this thing, beta, what is sine beta? Sine beta would be opposite side by hypotenuse. So the opposite side would be this length. What is this length? This length, if you want to figure out this length, you can find it out using this triangle. So this is nothing but L2 cos theta 2, and this length is L2 sine theta 2, and sine beta would be this length opposite side by hypotenuse, that is L2 cos theta 2 by R, and cos beta would be adjacent side by hypotenuse. Adjacent side would be this length, right? That is nothing but L1, sorry. This is L1 and this length is L2. Oh, sorry, I made a mistake. This should be L2 sine theta 2 and this should be L2 cos theta 2. Yes, so cos beta, so this is beta, cos beta would be adjacent side by hypotenuse. Adjacent side would be L1 plus L2 cos theta 2, that is L1 plus L2 cos theta 2. Now tan beta would be sine beta by cos beta, that is L2 sine theta 2 by L1 plus L2 cos theta 2. And if you take this arctangent, beta would be arctan or tan inverse this term. This is equation 6. So now we have obtained beta over here. We also have theta t. We have beta over here. We have theta t over here. You substitute both of these values into this equation, equation 4. So you'll be able to find out theta 1. So this is a fairly involved process. Okay, Murali, I've already said it. You can try it out. Yeah, it's a bit late. I didn't see that message. Yeah. So this is how you solve a inverse kinematics problem of this 2R robot. And there will be this is only for this specific underarm configuration. And for this overarm configuration, it basically varies slightly. These equations, derivations are more or less the same, but a few signs, plus and minus, gets interchanged. Yeah, and the final important thing that you have come across during these lectures is iterative numerical methods. But before going on to this, we'll discuss some of the few questions because I don't think we have enough time to discuss this. So few of the sample problems regarding week 3, you can expect similar problems during your assignments. So yeah, the first question basically says, in which configuration, which configuration will give a spherical workspace? So I hope you are familiar with this terminology. So this symbol means parallel. So the axis of these adjacent revolute joints are parallel, and the subsequent prismatic joint is perpendicular. So these sides are basically parallel and this is perpendicular. So what this configuration means is that we have two revolute joints in parallel. So one revolute joint, if you consider the axis of the revolute joint to be out of plane, we have one revolute joint over here. We have a link coming from the revolute joint. We have another revolute joint coming from here, right? And we have one prismatic joint that is perpendicular to the previous revolute joint. So if you have a prismatic joint like this, if we have a link, another link would be sliding like this. Sliding back and forth. So would such a configuration result in a spherical workspace? Because the 2RR robot can move only in a plane, right? 2RR robot with axes perpendicular to the plane can move only on the plane, and the prismatic joint can only cannot add anything or cannot add anything perpendicular. It will still make the robot move along the plane. So for a spherical workspace, we need a robot that is capable of three-dimensional motion. But with this configuration, it is only capable of planar motions. It's not capable to produce any motions perpendicular to the plane of the board. So obviously, the first answer is wrong. And what about the second answer? It says R perpendicular to R perpendicular to R. So again, we have three perpendicular revolute joints. Yeah. But again, like, do you think it can produce a spherical workspace? A spherical workspace is where the robot can locate its end effector within a section of a sphere. So basically, a sphere is sphere in this context is basically covered by an inner radius and an outer radius, and all the points within the sphere should be accessible by the robot. And if you are choosing the link lengths in a such a way, in a different way, this void may not even exist. You will also be able to cover this entire regions within the outer radius. Again, the size of this void depends on the link length. And the question is, would this configuration, the second configuration, be able to produce a spherical workspace? What do you think? Because it basically says we have three revolute joints, one revolute joint of perpendicular to the board, another revolute joint that is in some other direction, but perpendicular to the previous revolute joint, maybe like this. And we have one more revolute joint like this, coming like this. Would this be able to produce a spherical workspace? That is the question. Three revolute joints, R1, this is R2, this is R. And the answer is also, again, it's not possible because it can trace one surface of a sphere, but it cannot access all the points within a sphere, like all these points inside the sphere. It may not be capable. It can possibly rotate along one surface, or it can orient this end effector in any arbitrary orientation at a specific point. That depends whether the joint clearances are there or not. But again, the spherical workspace defined by this condition, where we have an inner radius, we have an outer radius of a sphere, and all the points within the sphere should be accessible. That condition will not be satisfied. And for the third case, this is a PPP robot, a prismatic parallel, prismatic parallel, prismatic. So prismatic along one direction, and another prismatic along a perpendicular direction, and one more prismatic along the third direction. So again, it should be fairly obvious that this robot would also not be able to produce a spherical workspace, but it can provide something of a cuboidal shape. A P parallel P robot can produce a workspace in the shape of a cuboid or in the shape of a rectangular prism or a square prism. This is what this P parallel P is capable of. And what about the fourth option? The fourth option being R perpendicular to R perpendicular to P. Would that be the correct answer? So the fourth option, I'll roughly draw the configuration of the robot. So if this is one link, and this is the axis of the first revolute joint, R1, and the second revolute joint is perpendicular to the first revolute joint. So this is R2. And we have a prismatic joint that is perpendicular to R2. So if this is R2, I'm taking this as perpendicular to R2. So the prismatic joint would go in this direction. Let this be D3. So would this be capable of producing a spherical workspace? Yeah, Murali has said it is possible. Yes, that is indeed correct. Because the robot can rotate about the first axis along this direction, the second axis along this direction, and the third axis along this direction. Does anyone have any questions regarding that? Yeah, this extendable rod, this extendable arm makes it possible for the robot to access all the points within the two bounds. So this is, if this is the upper bound, if the larger circle is the upper bound, and if the lower circle is the lower bound, and all the points within the both of these bounds would be accessible by the extension of this prismatic joint. And due to the fact that it can, the robot can rotate in two orthogonal directions, this is one direction and this is another direction, it can basically, the tip of this end effector can move in all the three directions. So the correct answer is indeed option D, right? Yes. If you want to check the answer, that is indeed the correct answer. Similarly, you can also verify the other remaining options, but again, it won't lead you to the workspace that is being asked in the question, spherical workspace. Okay, coming on to question 2. It says, select the correct statement regarding the representation of tool and effector frame. We have N, S, and A unit vectors as normal, sliding, and approach vectors. So from the lecture, from the summary that we have discussed, I hope you can recall. So if I'm drawing this as the plane of the gripper, we know the axis at which the tool is aligned would be the approach vector, APROACH, approach vector A. And the direction at which the opening and closing of the gripper would happen is the sliding vector S. This is the sliding vector. And the normal vector would be orthogonal to the sliding and the normal vector. That is, it would be orthogonal to the plane defined by the approach and the sliding vector. This is normal vector. And we also know how to construct a rotation matrix using this NSA unit vector. So the first column would be populated by the components of the n vector, nx, ny, nz. The second column would be populated by the components of s vector, that is sx, sy, sz. And the final column would be components of a vector, ax, ay, az. So with this, hopefully we can answer the question. It says to select the correct statement from the following statements. It says the normal vector is aligned with the tool axis and points away from the wrist. So is that correct statement or the false statement? Okay, Murali has actually said, can the fifth option comprising of this question, can it be spherical? It cannot be spherical because the difference is that, like, we have a prismatic joint over here and a revolute joint over here. So the prismatic joint makes it possible for the end effector to reach all the points within the two bounds, whereas the R joint does not make that capability. The prismatic joint is what is providing that capability. If it is R, if it was an R joint, it will only be possible to reach maybe one layer or one specific limited region within these two bounds. So I hope that is clear enough. Its prismatic joint makes you access all the points that is within these two spherical bounds. Okay, sorry for backtracking. So yeah, we have already established that the approach vector is going to be aligned in the tool axis. If this is how the tool is attached, it is the approach vector that is aligned with respect to the longitudinal axis. So obviously the first statement is false. And the second statement says n dot s is 1. Is that true? Because n and s are basically orthogonal vectors. So since those are 90 degrees apart, and the dot product between 90 degrees apart vectors are obviously going to be 0. In that regard, this is also false, because n s cos 90 is 0, right? That is what dot product is all about. Coming on to the third option, it says n cross a is 0. Again, that is also not true. N and a are orthogonal vectors, and n and a, just going by the magnitude, it is always going to be 1, because n and a are basically orthogonal 90 degrees apart. So n cross a is basically, magnitude is always going to be 1. It's not going to be 0. So again, that is also false. The fourth statement says the sliding vector is orthogonal to the approach vector and is aligned with the open and closed axis of the tool. So we have already established that is the correct thing. Like the sliding vector basically lies along the direction at which the gripper open and closes. So these are the jaws. If you extend the jaws along this direction, the gripper will open. If you extend or if you contract the jaws along this direction, it will contract. It will grip the tool. So this is a true statement. Sorry, the fourth statement is obviously going to be true. And fifth statement, it says n cross s is a. So if you can recall, like the first entry corresponds to the x-axis, the second entry corresponds to the y-axis, and the third entry corresponds to the z-axis. So it basically says n cross s is a. So by the right-handed rule, n cross s should be a. It should not be minus a. So this is also false. And the final statement says n cross a is s. So again, n cross a should be minus s by the right-handed thumb rule. So that makes the final statement to be false as well. So the only statement is the only correct statement is option 4, right? I hope that is clear enough. Okay, so moving on to question 3. This is a problem of inverse kinematics. It says for a spherical serial manipulator, the forward kinematics equations are as follows. So you are given the forward kinematics equation of a spherical manipulator in terms of x, in terms of y, in terms of z, where d1 is a constant, theta 1, theta 2, theta 3 are joint variables. So the question is, what is the value of d3 in terms of x, y, and z? So if you are given x, y, and z, you have to find out theta 1, theta 2, and d3, which are the joint space variables. So which of them is the correct answer? Is it option A? Is it option B? So yeah, d3, how do you solve d3? So what happens if you square x and y? So squaring the first two equations, x square plus y square would be d3 square cos square theta 1 sine square theta 2 plus d3 square sine square theta 1 sine square theta 2. So taking the common term sine square, what is the common term? It's theta 2, right? Sine square theta 2 common, it'll be, and d3 also is common. So d3 square sine square theta 2 times cos square theta 1 plus sine square theta 1. So this is going to be, this term is obviously going to be 1. So we'll take that as 1. So this is x square plus y square. So we have one more equation remaining. So if I take d1 to this other side, it will be z minus d1. And if I square this, we will get d3 square cos square theta 2. So if I'm adding these two equations, what will you get? X square plus y square plus z minus d1 the whole square. This would be d3 square sine square theta 2 plus d3 square cos square theta 2. So this is obviously going to be d3 square. And d3 is nothing but the square root of this expression. So that is fairly straightforward. So in that regard, the correct option is, I believe, option 5. Okay, again, I got a question from Murali. I seem to be missing the questions as I go through this. Uh, can I address it after we go through all the questions? Would it be fine? Hope so. Yeah, I'll try to come back because we are short of time, I believe. So yeah, this is how you solve this inverse kinematics problem of a spherical serial manipulator. Right. So the correct answer is option 5. Yes. Okay, moving on to question 4. Again, this is a sub-problem of the previous question. The equations are still the same. X is d3 cos theta 1 plus theta 2. Y is also, y and z are also the same. Now, the question is, we have to find out theta 2 in terms of x, y, and z. How do you find theta 2 in terms of x, y, and z? So how do you manipulate these equations? So yeah, equations 1 and 2 has theta 2 in common. You cannot divide them because if you divide them, theta 2 will get cancelled. So what to do? If I square and add the first two equations, x square and y square, what will we get? X square plus y square would be d3 square cos square theta 1 sine square theta 2 plus d3 square sine square theta 1 sine square theta 2. So taking the common terms d3 sine theta 2 as common factors, x square plus y square would be d3 square sine square theta 2, and the remaining terms are cos square theta 1 plus sine square theta 1. That is obviously going to be 1, so I'm removing that term for the time being. And we have the remaining term in z, that is z equal to d1 plus d3 cos theta 2. So what can we do? Okay, so I'm labeling this as equation 1 and this being equation 2. If I do further manipulations on equation 1 would imply square root of x square plus y square would be d3 sine theta 2. And from equation 2, you would get this equation z minus d1. This would be d3 cos theta 2. So I'm labeling this as equation 3 and equation 4. And dividing equation 3 and 4, equation 3 by equation 4 would yield you tan theta 2 would be square root of x square plus y square divided by z minus d1. And theta 2 would be tan inverse x square plus y square, the whole under square root divided by z minus d1. So this is the inverse kinematics expression for theta 2. Right. So in that regard, the correct answer is option. What is the option? I guess it's option B. In that regard. Yes, that is indeed correct. Okay, moving on to equation question 5. This is a true or false question. It says, okay, it says the inverse kinematics is the transformation of kinematic information from joint variable space to Cartesian coordinate space of the final frame. So as per the DH approach, the inverse kinematics is basically transformation matrix multiplication. Is that true or false? So like for an n-link manipulator, we can assemble this transformation matrix from 0th frame to the first frame, first frame to the second frame, from second to the third frame, and all the way from n-1 frame to this nth frame. So if you multiply all these transformation matrices individually, you will be able to get the pose of the final frame, that is n, with respect to the pose of the 0th frame or the base frame. So what you are doing for forward kinematics is you are simply multiplying the individual transformation matrices successively, right? So that makes the statement to be true because it says, sorry, it says it is regarding inverse kinematics. So is it true or false? Because this is basically forward kinematics, because what expression you are obtaining, because each of these transformation matrices would be functions of the joint variables, joint space variables. For example, this would be function of theta1, this would be function of theta2, this would be function of theta3. And finally, the final assembled transformation matrices would be function of theta1, theta2, etc., theta n. Right? And if you are giving theta1 and theta2 as inputs, what you obtain as 0t1 is basically the final configuration of the robot. So that makes it false because this is basically regarding forward kinematics, not for the inverse kinematics. The forward kinematics basically deals with the matrix transformation of the transformation matrix. Are you guys following this? Because we have already covered this during the summary. How to assemble the DH matrices. Okay. Yes. Okay. Thank you. Okay. So indeed the answer is false because it's not relevant to inverse kinematics. It's relevant to the forward kinematics. Okay. Again, moving on to question 6. This is also a similar inverse kinematics problem. So you are again, like just as we seen in the previous question, you are being given the X and the Y positions of a robot. And here this is a planar polar robot. A planar polar robot where the equations, the forward kinematics equations are X is d sine theta and Y is d cos theta. So we have already seen that in one of the examples, that is nothing but an RP robot, where the variables d and theta are joint space variables. And the question asks you to find out the inverse kinematic solution. Like for a given X and Y, what are the parameters d and theta? Like we have already figured this out earlier, but just for the sake of completeness, I am delivering this. X is d sine theta, Y is d cos theta, and squaring and adding x square plus y square is d square, and d is nothing but square root of x square plus y square. And if you let this be equation 1, and if this is equation 2, if you are dividing equation 1 by equation 2, yeah, this would be x by y would be sine theta by cos theta. This would be tan theta, and theta would be tan inverse x by y. Yeah, typically we would expect it to be y by x, but this is x by y because it is given as x is d sine theta and y is d cos theta. So in that regard, the correct answer would be option C. Because it depends, because for a robot, for an RP robot, if this is an R, and if there's a prismatic link also here, if you label it as, if you label x and y axis like this, if this is the x axis and this is the y axis, And if this is how you measure theta, right, it depends on how you label the axis, you will get these equations, tan inverse x by y. But if x and y axes are alternated, like if this is y and if this is x, you will get this equation, right? And we have to be careful regarding how these equations are basically. So in this regard, the correct answer is option C. Okay, that is indeed the correct answer. Okay, so moving on to question 7. This is in continuation, in line with the topics that we have discussed last week. This is regarding the DS parameters of the second joint. So basically we have how many frames? We have 4 frames. We have the 0th frame. We have a coincident first frame. The 0 and first frames are over here. We have frame 2. We have frame 3. And how many joint variables do we have? We have theta 1 as a rotary joint variable. We have theta 2 as again a rotary joint variable. We also have theta 3 that is also that is not a rotary variable. In fact, that is a prismatic joint variable. So you are asked to find out the DS parameters for the second joint. So how do you find that out? So you know the DS parameters to be alpha I minus 1. You have a I minus 1. You have theta I. You have di for given I. So for I equals to, what is alpha I minus I? So alpha I minus I is alpha 1. Alpha 2 minus 1 is alpha 1. That is the angle at which you should be rotating about x1. The angle at which you should be rotating about x1 such that z1 and z2 would be parallel. So since z1 and z2 are already parallel, you don't have to rotate it by any amount because these are already parallel. So you don't have to rotate by any amount with respect to x1 axis. So alpha I minus 1 is indeed going to be 0. And what is ai minus 1? Ai minus 1 is basically the perpendicular distance, the distance that you have to move along x1 so that the perpendicular distance between z1 and z2 can be taken care of. So if this is z1 and if this is z2, the perpendicular distance between z1 and z2 is given by this distance, that is a1. And you have to move along x1. You have to move a1 units along x1 so that the perpendicular distance between z1 and z2 vanishes. So ai minus 1 in this regard would be a1. And what would be theta I? So theta I would be the angle at which you would rotate. You have to rotate about z2 because the index basically changes from I minus 1 to I. So theta I corresponds to the angle at which you have to rotate along z2 so that x1 and x2 axes would be parallel. And what would that be? Because it may appear in this equation that x1 and x2 are parallel. But since this is an active joint, since this is an active revolute joint, it can rotate about this vertical axis. So at some other instance, the x-axis could be here. At some other instance, it could be here. It could be here. It could be here. It could be at any other orientation parameters by the variable theta 2. So if x1 is aligned like this, and if x2 is aligned, if x2 is rotated by an amount theta 2, you have to rotate x1 by an amount theta 2 along z2 so that x1 and x2 will become parallel. So in that regard, theta I would be 2. Now one more parameter is there, di. So di is basically the distance you have to travel. You have to traverse along Z2 so that the perpendicular distance between Z1 and Z2 vanishes. So the perpendicular distance between Z1 and Z2 is D3, right? I guess it's, yeah, sorry, it's D2. It's D2. The perpendicular distance between is X1 and X2 is D2. So you have to traverse distance D2 along Z2 so that this distance would vanish. So in that regard, DI would be D2 for the second joint. So in that regard, our DS parameters are 0, A1, theta 1, and D2. And the correct answer would be option B, I suppose. It is 0, A1, theta 2, and D2. Yes, correct. Saurav has responded. Okay. Yes, in that regard, the correct answer is D2 itself. And moving on to question 8, this is also a similar problem. It says for a given diagram, find the DS parameters of the second joint. Again, the second joint. So this is the 0th joint attached to the ground frame. This is the first, okay. Yeah, that is the first joint attached to the first frame, and this is the second frame attached to the second link. So again, the 4 DS parameters are alpha I minus 1, AI minus 1, beta I, DI, and we have our I as 2. So what would be alpha I minus 1? So if you want to move from the first frame to the second frame, now these are a distance apart actually. These are a distance apart, and it's also said that second joint is a active joint. So second joint is an active joint with the joint variable theta 2, and the axis of the active revolute joint is along Z2. Right? So at one instance, X will be here. At another instance, X can rotate like this, it can rotate like this, it can rotate like this, it can rotate like this, depending on theta 2. So the first term, alpha I minus 1, is basically by how much of an angle you have to rotate about X1 so that Z1 and Z2 would be aligned. So Z1 is along this axis, Z2 is along this axis. You have to rotate by an amount of 90 degrees along X1 so that Z1 and Z2 would be aligned. Right? So you have to be careful, you have to be mindful of the sequence. The first is rotation along X1 so that Z1 and Z2 will be aligned. Right? So if you want, I can draw the steps actually. So this is Z1, this is X1, this is, sorry, this is Z2, this is X2, and let this distance be A1. And the first sequence is to rotate about X1 by an amount 90 degrees. So if you rotate about X1 by 90 degrees, Z1 would come out of plane like this. This would be Z1. Now, as you can see, Z1 and Z2 are basically aligned. So since we rotated by 90 degrees, alpha I minus 1 would be 90 degrees. And the second term, AI minus 1, is nothing but by how much distance you have to traverse along X1 so that the perpendicular distance between Z1 and Z2 vanishes. Basically, it's nothing but by how much distance you have to travel so that these two axes coincide. The distance between these two axes vanish. As you can see, you have to move by an amount A1. So if the distance between the first and the second frames is A1, you have to move by a unit A1 along X1 so that the distance between Z1 and Z2 vanishes. Right? So we move by a distance a1, so that makes ai minus 1 to be a1. So after this transformation, the distance between these two is 0. I am just simply drawing a physical distance just to make it clear. But as of now, since we have made this transformation, these two frames are basically coincident at the moment. Like Z1 is coincident with X2. Sorry, Z1 is coincident with Z2. X1 is coincident with X2. Both of these frames are coincident. There is no physical distance between. Yeah. And the third term is theta I. It basically says by how much of an angle you should be rotating about Z2 so that X1 would be parallel with X2. Right? And due to the fact that this is an active joint, theta 2, this X2 can be at any location. X2 can be like this specific location is only for representative purposes. But in reality, the orientation of X2 can be along any of these directions. And X1 is only along this direction. And if you want to match X1 and X2, you have to rotate by an amount theta 2 about Z2. Right? So that becomes theta I becomes theta 2. Now the distance between this frame and this frame 1 and 2 is 0. Z1 and Z2 are basically aligned. X1 and X2 are also aligned. Now the final parameter di is by how much units you should be moving along Z2 so that Z1 and Z2 are coincident. So basically they are already coincident. They are already coincident and there is no need for you to move along Z2. There is no further need for you to move along Z2 because they are already coincident. So that makes di to be 0. Right? So yeah, in that regard, the correct answer is pi by 2, a1, theta 2, 0. And the correct answer would be option B, I guess. Pi by 2, a1, theta 2, and 0. Yes, option B. And question 9 is also a true or false question. It says one of the advantages of numerical solutions to inverse kinematics is that it returns all possible solutions. Is this true or false? It says numerical solution and it says it also returns all possible solutions. So Saurav has responded it to be false. Murali has also responded it to be false. That is indeed the correct answer. Because numerical results can only converge to a specific solution. And that also depends on where you start your initial guess. So I guess that is fairly straightforward. No need to further discuss on that. And for question 10, it says, yeah, the number of operations to solve inverse kinematics analytically is always constant. Is this true or false? Solving inverse kinematics analytically, do we know how many number of equations, how many number of operations to solve? That is, Murali has responded it to be true. Saurav also has responded it to be true. So that is indeed the correct answer. Because since it is analytical, we know exactly how many operations that we require. And that will also give you a picture of the computational time of solving it analytically. But in case of numerical, it's kind of a black box. We don't know how many operations that is going to happen or how many operations happens in the background. So that gives a vague picture of it does not give a clear picture of the number of operations, and hence we cannot say much about the computational time as well. That is indeed true. Yes, and this is the final question basically, again, based on DS parameters, an example problem on DS parameters. It says find the DS parameter for the third joint. So over here, we have the third joint. You have to find out the DS parameter for the third joint. So again, we have the 4 DS parameters to be alpha I minus 1, AI minus 1, theta I, BI. Yes, and for I corresponding to 3, could anyone of you solve this time? What would be the answer? What would be alpha I? So this is Z2 and this is Z3. Z2 is basically out of plane. It's away from the plane, out of plane, away from the plane. And Z3 is in the plane and also vertically up. Okay, so Murali has said alpha I to be pi by 2. So alpha I basically denotes by how much of an angle you have to rotate about x2 so that Z2 and Z3 would be aligned. So Z3 is like this, x3 is like this, and over here we have Z2 and we have x2 like this. And it also says that the third joint is an active prismatic joint. So the distance between the second frame 2 and the third frame 3 basically varies. This is a varying distance d3. So the question says alpha I is by how much of an angle you have to rotate about Z2 so that Z3 and Z2 are parallel. So it's obvious that if you rotate about Z2 by 90 degrees, Z2 and Z3 would be aligned. So alpha I minus 1 would be pi by 2. So what will happen to Z2? Z2 would now be aligned with respect to Z3. So yeah. Now the new Z2 would be somewhat like this, Z2, since we have rotated 90 degrees. Now what does AI minus 1 say? AI minus 1 is basically the perpendicular distance along x2, perpendicular distance along x2, such that the distance between Z3 and Z1 vanishes. And what is AI minus 1? Can anyone of you respond? It is nothing but the distance you have to move along x2. So Murali has said that to be 0. Saurav also it's said it to be 0. Yes, because there is no, the perpendicular distance between Z2 and Z3 is virtually 0. It's essentially 0. And you won't gain anything if you move by any amount along x2. So that is indeed 0. Yeah, so since there is no transformation, this is 0. The current Z2 and x2 remains as such. Now, what about theta I? Theta I is basically the angle or the amount by which you have to rotate about Z3 so that x3 and x2 would be aligned. Okay, so both of you have responded it to be theta 2. It's not theta 2 because Z3 is a prismatic joint. Z3 is a prismatic joint actually. And x3 will always remain parallel to x2, right? Because it's a prismatic joint. There is no rotation about Z3. Because like Z3 can only move up and down. It can only move up and down. It cannot rotate by any amount by Z2. So the correct answer is 0 in that regard. Is that clear? Because Z3 is a prismatic joint and the variable that is associated with theta I would be a joint variable in terms of the prismatic joint. And Z2 and Z3, we have already made it aligned with respect to this alpha I parameter. We are using this theta I so that x3 and x2 would be aligned. But x2 and x3 are already aligned because The third axis is nothing but a prismatic joint. X3 is always going to be as such. It is only this distance that is going to vary, right? So in that regard, theta I is 0. And what about di? Di is the perpendicular distance between x3 and x2 along Z3. So what would that be? Di would be the perpendicular distance between x3 and x2 along Z3 in the direction of Z3. Yes. Now that is D3, as Murali have said. So this is how we work around with this DS parameters. And in that regard, the correct answer is pi by 2, 0, 0, D3. It's pi by 2, 0, 0, D3. The correct answer is option B. Yeah, we have reached the quota of our tutorial questions. You can expect similar questions for your assignments. If you have any doubts, please let me know regarding anything what we have discussed so far, any questions that we have discussed so far. I think Murali had a, yeah. What was the question actually? If the gripper has a rotary open close fingers, then the rotary axis is parallel to N. No, like it's not that straightforward, because like in case of a gripper like this, what you have mentioned is correct only because, one second. Yeah, in case of a gripper like this, what you have mentioned is correct only because the rotation of the revolute joint would be, it could be along any other direction. But the motion of the gripper, the sliding, the back and forth sliding of the gripper would be along a different direction. In this case, it would be along this direction. And the motor to actuate the gripper can be in a different direction. And using gears, you can actually make the gripper move in a different direction. So that makes it the sliding vector to be along the direction at which the gripper moves back and forth. Or if there is a confusion regarding the definition of the sliding vector, it is always better to first identify the normal vector, because the normal vector is always going to be perpendicular to the plane of the gripper. So if it is a planar gripper, it could be the normal vector would be perpendicular to the plane of the gripper. And we also know the approach vector to be along the longitudinal axis of the tool and perpendicular to the plane comprised by the normal vector and the approach vector. And while obeying the right-handed thumb rule, you can also define the sliding vector. So that is also another possible alternative. So instead of defining these two first and then defining the normal vector using the right-handed thumb rule, you can define these two first, the normal vector and the approach vector, and using the right-handed thumb rule, you can define the sliding. It depends actually. It depends on the application. It depends on the capability of the gripper, things like that. So is there anything any one of you would like to further discuss? Any doubts that you would like to get clarified? Any questions that is not clear enough? Okay. Okay. Thank you. Okay, I'm getting some questions from Dheeraj. Could you open your mic actually? The location at which a coordinate frame is attached to a rigid body multi-body system as per non-standard. Is this an assignment question? Is this an assignment question or is this discussed in the tutorial? If this is an assignment question, I cannot discuss. If this is an assignment question, I cannot discuss that in. Okay. Okay, so yeah, it says the deadline is completed. Can anyone of you verify that? Is it completed? Is the deadline of assignment 2 completed? Uh, okay, so like, I don't know, but anyway, like since you have raised this question, I'll answer it anyway. So yeah, there are, as you know, there are like if no, if others does not have any further questions, you can log out. If you wish to stay, you can stay, no problems. I'll just complete this answer actually. So you have a link over here and you have two conventions. So I'll replicate this thing. So we have two conventions, a standard DH convention, and we also have a non-standard DH convention. And we are basically following the non-standard DH convention throughout this course, for this entire course. And the question basically says the location at which the coordinate frame is attached to a rigid body in a multi-body system as per non-standard DH parameter conventions. So like as per the DH convention, as per any DH convention, we have to attach a frame on a rigid body because rigid bodies are represented using coordinate frames, frames of references. And one more thing before getting on with the terminology, there are two words that is basically defined. It's something we call as proximal and distal. And proximal is the end that is nearer to the base, and distal is the end that is nearer to the end effector, in the direction of end effector. So if this is a link, if these are links, if base is over here and if end effector is over here, and similar for this case also, base is over here, end effector is over here. The side closer to the base is called proximal, and the side closer to the end effector is called distal. Same goes for this also, proximal and distal. And as per the standard DH convention, we attach the coordinate frames on the proximal end, sorry, on the distal end actually, as per the standard. This is the frame. We attach the coordinate frame on the distal end for the standard DH convention. And for this non-standard DH convention, we attach it on the proximal end. So that is the difference actually. Yeah, that is the question. And Sahil as, okay, Murali, thank you. You can log out. And regarding the video, you can actually get the recorded session. It's already shared in the website, right? It's already shared. All the links and the lecture notes that I'm currently sharing with you, they're all shared in the website. Let me see if I can get it for you. So if you log into this NPTEL website and it should be there once. If you go to this course, let me share my screen. Yeah. Okay. Can you see my screen? I don't know. Yeah, I hope you can see my screen. If you go to this course, at the end of this outline, you can actually see problem solving session, problem solving recordings. And if you click on this, you have a link actually. And if you again click on that, yeah, you can access all the links. So I have uploaded the videos for week 1. I have already uploaded the video of week 2, and the presentation folder will give you access to the slides also. I hope that is clear. Okay, yes, okay. So if there is nothing else, shall I log out? Yeah. Okay. Okay. Thank you. Mm.